As you might have noticed in the first video for today's lesson, that as n gets bigger and bigger, as more and more observations are taken in your binomial setting, calculating the binomial probabilities associated with your situation gets more and more tedious, just because you have to calculate the probability for each and every outcome. Now, using your calculator can make that a little bit easier, or using some sort of statistical software can make it a bit less time-consuming. But it turns out that we can actually use the normal distribution to approximate the binomial distribution when n is large, because as n gets larger and larger, the binomial distribution begins to behave more and more like the normal distribution. There are some requirements that have to be met, though. First, this can only be used, this normal approximation, when n times p and n times 1 minus p is going to be greater than or equal to 10. That's just the general rule of thumb that you need to keep in mind. If n times p or n times 1 minus p is not greater than or equal to 10, then you should not use this approximation. You should just go about doing your binomial probability calculations as you normally would. However, if that requirement is met, then when n is large, we know that our binomial distribution of x will behave approximately the same as the normal distribution. So we can use we can use our binomial mean, which is NP, to represent or to step in for the mean of the normal distribution, and we can use our binomial standard deviation, which is the square root of NP times 1 minus p, to be representative of the standard deviation of the associated normal distribution. Okay, so I want to do an example of when you would use this normal approximation for a binomial distribution. So this, what I've written on the slide, comes from an example on page 527 in your book. And it says, I'm reading from the book, not from my slide, of course. It says, our attitudes toward shopping changing. Sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agreed or disagreed with the statement, I like buying new clothes, but shopping is often frustrating and time-consuming. The population that the poll wants to draw conclusions about is all U.S. residents aged 18 and over. Suppose that in fact 60% of all U.S. residents would say agree if asked the same question. What is the probability that 1,520 or more of the sample agree? So let's summarize. We're trying to figure out whether our attitudes toward shopping are changing. We think that people used to like shopping, but now we think that people are getting frustrated. So the statement that they were asked if they agreed with was, again, I like buying new clothes, but shopping is often frustrating and time-consuming. We think that overall, if we surveyed the entire American adult population, that 16% of all adults would agree with this statement. We want to know that out of our random sample of 2,500 people, what the probability is that 1,520 or more of them will agree. Now, this is an awfully large sample. We really don't want to have to calculate each and every individual probability from 1,520 all the way up to 2,500 for our binomial setting. So instead, what we can do is see if the normal approximation would be appropriate here. So first off, we need to confirm that n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10, just so that we can be sure that it would be appropriate to use the normal approximation here. Well, in this problem, n is 2,500 and p is 60% or 0.6. And that is most certainly greater than 10. So that requirement is met. And on the other side, we've got 2,500 times 1 minus p, which is 0.4, and that is also going to be greater than 10. So it would be appropriate here to use the normal distribution to approximate this binomial distribution. Okay, so now that we know that, what we need to do is we need to calculate the mean and the standard deviation for our distribution. And we are going to use the formula for the mean of a binomial and the standard deviation of a binomial distribution. So we know that the mean is calculated by multiplying n times p. So that's 2,500. Very neat. 2,500 times p, which we just said was 0.6. And then the standard deviation is the square root of 2,500. I'll write out the formula, sorry. That's np times 1 minus p, which is the square root of 2,500 times 0.6 times 0.4. So it turns out that the mean for our binomial distribution is 1,500, and the standard deviation is 24.49. Now, like we said, because it would be appropriate to use a normal approximation here, what we're going to do is we're going to use that mean and that standard deviation that we just calculated, but we're going to use them in the context of a normal distribution. So that means that we need to calculate the z-score that's going to be associated with the data point that we're interested in. So we need to do a little review of how to calculate a z-score. Z is x minus x bar, or x minus mu, I guess I should say in this case, x minus mu over our standard deviation. In this problem, x is 1,520, because we want to know what's the probability that 1,520 or more agree with our statement. So we need to plug that into our z-score formula. So we're going to have 1,520 minus our mean of 1,500. We're going to divide that by our standard deviation of 24.49. And that's going to give us a z-score of 0.8167. So that means we can go ahead and sketch out our normal curve. And our z-score that we just calculated was 0.8167. So if here's 0, 0.8167 will be about in this range. And again, we are trying to calculate the probability that we would be at or above this z-score. So we're trying to calculate the area that is to the left, or excuse me, to the right of that z-score that we just found, which I just shaded in green. And we can do that on our calculator, like I showed you earlier in the year. So we are again calculating the probability that x is greater than 1,520. And when I do that, I get about 0.2071. So approximately 20.71% of our survey respondents would agree with our statement.